Hey guys, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to look at yet another method for solving the explore-exploit dilemma. These are all important parts of the reinforcement learning literature, though it may seem we're being a little too thorough. The main idea behind UCB1 is confidence bounds. Intuitively, you know that if we collect 10 samples and take the mean, this is not as accurate as when you collect 1,000 samples and take the mean. If you were to draw a confidence bound around each mean, you would draw a much wider bound around the 10 sample mean and a much skinnier bound on the 1,000 sample mean. In statistics, there is a bound called the Chernoff-Hofding bound, and it says that our confidence bound changes exponentially with the number of samples we collect. The bound looks complicated, but it becomes less complicated if you read it out slowly. It says that the probability that the absolute difference between the sample mean and the true mean is greater than or equal to epsilon is less than 2 times the exponent of minus 2 epsilon squared times n, where n is the number of samples collected and epsilon is just an arbitrary small number. The details are outside the scope of this course, but the algorithm is just as simple as the others we've looked at. The idea is, we take the upper confidence bound to be the regular sample mean plus the square root of 2 times ln n divided by nj. This is equivalent to choosing an epsilon equal to the square root and everything inside it. So let's talk about what these symbols mean. X bar j is just the regular sample mean of the jth bandit. N by itself is the total number of times you've played all the bandits. N sub j is the number of times you've played the jth bandit. Now, how do we use this formula? Well, the idea is similar to the optimistic initial values method. We use the greedy strategy only, but what we're greedy with respect to is not just the sample mean, but the upper confidence bound of the sample mean. The question is, why does this work? Well, the confidence bound seems to be the ratio of two things, n, which is the total number of times you played, and n sub j, which is the total number of times you played bandit j. So if you played some other bandits many times, but nj is small, then this ratio is going to be large, which would make the upper confidence bound higher, which would cause you to select this bandit to play. At the same time, if nj is large, then the ratio is small, at which point the upper confidence bound will shrink. But one key point about this ratio is that the top part grows with the logarithm of n, which means it's going to grow more slowly than nj eventually. That means, as you play all the bandits more and more, the upper confidence bounds will shrink, and you'll only be using the sample means, which is okay since you've collected lots of data. So this also converges to a purely greedy strategy, based on only the sample means. Let's look at some pseudocode so we can understand how this works better. It's essentially just as simple as the optimistic initial values method. We're just replacing the formula that goes into the argmax, which is now the upper confidence bound. Note that there is a small problem where this formula doesn't work if nj is 0. To fix that, you can simply add a small number to the denominator. If you don't want to try to code this yourself, the relevant file in the course repo is UCB1.py. Let's now look at the results. Okay, so this is epsilon greedy. And this is UCB1. Okay, so we see that eventually UCB1 outperforms epsilon greedy.